This PowerPoint YouTube video is about my midterm questions and answers. Okay, the first question. Use master theorem to find out the asymptotic bounds for Tn equals 16t in parentheses n over 4 plus n squared. Okay, so using the master theorem, we know Fn equals n squared, and A equals 16, B equals 4. So n log BA equals n squared. And because the F term is comparable to the recursive term, so case 2 of the master theorem applies, and the time course is big theta, n squared log n. And we try to use substitution method to prove this asymptotic bounds. Okay, so in order to remove the recursive t terms on the right hand side here, I have to times the equation 1 with 16 and times 16 squared to the equation 2, and then until I reach equation k, that's a 16 to the power of k times t1 equals 0. Then I add all of them. I get Tn equals n squared plus 16 times n squared over 4 squared plus 16 squared times n squared over 4 to the power of 4. And after a few steps, then finally I get Tn equals n squared times log n. So this is the same results we get as we get using the master theorem. Okay, question 2. Okay, so use master theorem again to prove or solve this to find out the time course. All right, so F term Fn equals 5n, and A equals 1, B equals 19 over 3. So n log BA equals n to the power of 0. That is 1. And here the time, because the F term is greater than the recursive term. So F term is dominant. Then case 3 of the master theorem applies, and the time course is big theta n. Okay, and this is question 3. To sort the telephone numbers of a major carrier. And what type of sorting algorithm will I use? And give some justification. All right, so in this question, to solve a list of telephone numbers, I would use linear time sorting. And among the linear time sorting, I would choose radix sort because it's fast and the code is simple. So the reasons first is because linear time sorting is faster, and then when we compare to the sorting algorithms based on comparisons such as quick sort, insertion sort, merge sort and heap sort. We know the time cost for these sort is either n square or n log n, and n square and n log n is greater than the time cost for linear time sorting, because in linear time sorting, the time cost is n. Okay, so when we look at linear time sorting by itself, we know linear time sorting algorithms includes counting sort, bucket sort, radix sort. And for this counting sort, we know, for example, here, so we have the 10-digit. Then we need to, how do I say it? We need to have a large memories, because we have to convert all the numbers index that requires a large memory. And while this bucket sort, we know it is mainly used to sort floating points numbers ranging from 0 to 1. And then therefore this radix sort choice to sort a list of 10-digit numbers. We need to run the linked list 10 times only. A list of 10-digit numbers of telephone numbers to be sorted. And the time cost again here is n. So that's why I pick radix sort as the sorting algorithm to solve this problem. Okay, so then question 4. Question 4 asks us to modify the text portion of two-way merge sort into a new algorithm of merge triple sort. So merge triple sort is kind of like 3 ways merge sort. And so this is the original code in the textbook, page 31. So in order to divide the 2 subarrays into 3 subarrays, we need to have Q1 and Q2 to segregate the subarrays. The framework is basically the same as the code of two-way merge sort in the textbook. So part 2 here. Let's see, part 2 here. Oh, all right. I'm sorry. So actually, I just add Q1 and Q2 into this array to compute the size of 3 subarrays. And then I have N1, N2, and N3. So N1 would be the last element of the new subarray N1. And then N2 is the last element of the another subarray. And then N3 is element of, oh, I'm sorry, no. Here I'm counting the size of the subarrays. Yeah, so N1, N2, N3 is the size of the subarrays. Each of them are 3, or maybe 4, 6, 5, either way. Depends on the numbers of the number of elements. Okay. Other parts are just very similar. I said the framework is basically the same, except we just have to copy the elements from array to 3 subarrays, merge the elements of the subarrays. Okay, all right. So then this is question 4b. Question 4b is to find the asymptotic bounds or running time of merge triple sort. So for merge triple sort, the recursive description is this: Tn equals 3t, open parenthesis, n over 3 and close parenthesis plus n. So if we use the master theorem, we know Fn equals n here, and A equals 3, B equals 3 again. So n log BA equals n. And so this F term is comparable to this recursive term, so that case 2 of master theorem is applied. And the time cost is big theta, n log n. So then I use substitution method to validate the answer again. So the answer is again n log n. All right. Next question is to modify the pseudocode of consort algorithm on the textbook, page 195, so that an input array of numbers in the range of -n to n can be sorted. Okay, so we know the code in the textbook here actually is the same as my the code in my part 3 here, part 2, sorry, part 2 from here to here. And this part of code requires the value of numbers to be non-negative. So in order to change the code, the numbers, or change the code to workable, we need to pre-process array A to make all the elements non-negative. So in part 1 here, I shift the elements into non-negative. So the code I use is for I equals 1 to and the last element of array A, AI equals AI plus n. Then part 2, as I said, is the same. The code is the same as the code in the textbook. Then after the sorting, we need to shift back to the original values. So here in part 3, I have 4, I equals 1 to the last element of array B, Bi equals Bi minus n. Okay, so for question 6, this is the same concept as the way I solve question 5. So we know bucket sort is applicable for array elements with values ranging from 0 to 1, that is the floating point numbers. So in part A, or part 1, sorry here. So in part 1, I shift and scale the original array A. So the code is I equals 1 to the last element of array A. AI equals a parenthesis. Within the parenthesis, we have 50 plus 8j, and then divided by 100. Then, oh, I'm sorry, this should be AI, not AJ. Okay, and then the code again, the part 2 is the code in part 2 here is the same as the textbook here. Then after sorting, in part 3, we shift and scale back to the value of the original array's elements. So I use for I equals 1 to the last element of array A. AI equals AI times 150. And so that this the value can be, the range of the value can go back within negative 50 to 50. Right, so that's the end of my presentation. Thank you very much.